Hello. So we are continuing on with chapter 2 on quadratics. And in this section, we're not particularly going to look at quadratics specifically. We're actually going to look at something called functions. And you would have seen this at GCSE. It's essentially this sort of notation, right? Which we call f of x. So on a very simple level, then, we have an input, right? Which we normally call x. Then we do something to it to then get an output, which to get an output. And this thing that we do, these sort of operations, is our function, right? F of x, right? So we apply some sort of operation to get an output. So you plug something in to a function, and then the function we work with it, and then we get a number at the end. So as an example, say with x, then if we want to square it, then the result will be x squared. Okay. And so how we express that as a function? Well, we take an input x. So we plug in x to f of x, and then we want to do x squared, okay? And then what this tells us is if we plug in the value of x, then we plug in x into here and then square it, and the result will be the square of the number. Okay, so for example, if we plugged in f of 5, for instance, then this function telling us we need to do 5 squared, which would then be 25. So our input in this case would be 5, and our output would be 25. Okay. As another example, it doesn't have to just be x squared. You can either do something like sine or trig. So say instead we have an input x, and then we want to do the sine of it. So we do sine of x. So we plug in x, whatever number at input. So plug in our input, a value of x. Then we get out the sine of it. So for example, if we were to do put an input of like 90 degrees, right? We plug in 90 to our function, and then our function calculates the sine of it. Okay, so we have sine of 90, and then we evaluate that. Well, sine would be 1, wouldn't it? Sine of 90 would be 1. You could put that in the calculator, but ideally, if you know the graph, you should be aware of that. But we get 1, and so in this case, our input would be 90 degrees. Oh, and our output would be 1. Okay, so hopefully you see what we're doing here. We get an input, then we plug it into our function, and then our function determines what we do with it, and then we plug that value in, then we get an output. Okay, so we go from an input to an output. And so we express that as a function of f of x, right? Where we plug in our value of x, and then we get back out what the function is telling us. So if we want to square it, in this case we do x squared. If we want to take the sine of it, we can do we'll do the sine of the value. And that's essentially what it is, right? Without overcomplicating it. That's what we do. And then we usually call x then the input, and then our output will be the f of x. So when we plug in our x, what do we get out of it? And that's essentially all it is. And more specifically, instead of using input and output, the word we use is the mathematical word is called a domain. So the domain is essentially the input. So the values of x that we plug in to a function. So it's essentially the same thing. We just use domain as the language, and likewise the output we call the range. Okay. So in other words, the range of values we get out of the function when we plug in values of x, that's our range. Okay. So as an example, again, say if we had f of x to be x x cubed, let's say. No, let's do minus x cubed. There we are. Well, again, our input would be x. So, but instead, say if we were plug a domain was 6. that's what our input would be. So we'd have f of 6. Well, that'd be minus 6 cubed, right? And then that our 6 cubed. Let's do it simple. 2. There we are. 2, and then minus 2 cubed. Well, that'll be minus 8. So minus 8 would be the range there. Okay. So it's essentially the same sort of idea, right? The domain is the input, the range is the output. So that's the sort of language we use with functions, but that's essentially all it is, okay? And actually, it's very, very helpful to consider stuff graphically. So, for example, here with x squared, hopefully we know what the x squared graph looks like. Something like this, right? Well, actually, what the domain is essentially the x values, right? So if we have x and y, this x-axis here is our domain. It's the range of values that we plug into our function, which should be f of x is x squared, right? Then our y, what we get out of it when we plug the value in, that's our range, okay? So in other words, the y values is our range, okay? It's sort of like the y-axis. So yeah, that's essentially all it is, right? The domain are the values of a function f of x, or g of x, or h, or whatever, what letter you want to call the function. I would call it f of x normally. The domain is essentially the values of x we plug into it, and then the range is what we get out of it. So again, as an example for x squared, x is our domain that we're plugging in, and then our range is the numbers we get out of it, so the squares of it. Okay, the squared numbers. And yeah, that's essentially all it is. Uh, with regards to functions. So the core idea you need to know function is we can use this language f of x, where we plug in a value of x, which is our domain, and then a function, for example, if it was x squared, we would have to square the number, and then that'll give us our range. Okay, and that's essentially all you need to know. But there's also okay, but there's also something else we need to look at. More types of language and notation. And that is, you're going to probably see this sort of symbol here. X is an element of R. And we'll discuss this in a minute. But before we do that, we need to look at some certain symbols that you'll come across in your A level. And it's these 4 symbols here. And what these 4 symbols are, they are basically the main types of numbers we work with. Okay, they look like a really weird symbol, really weird letter, but these 4 are basically different types of numbers. And so let's go through it then. So n is what we call natural numbers. Okay, these are basically positive integers. So these are basically the list of numbers 1, 2. I'm going to need to probably get rid of this. 1, 2, 1, 2, 3, 4, and so on. You can include 0, as it's not strictly a negative number. 0 is not negative; it doesn't have a negative sign attached to it. So you can call it 0, 1, but the whole idea is right with not getting that fiddly. It's essentially the list of positive integers, right? Positive whole numbers. So it goes from 0, 1, 2, 3, 4, 5, 6, so on. These are natural numbers, okay? And then we can actually generalize a little bit more, and it's Z, which is integers, right? This Z means the integers or the list of integers. And so these are whole numbers, but they can be negative as well. So that can go from, well, negative infinity in a way, but we can go to say like -3, -2, -1, 0, 1, 2, 3, and so on. Okay, so it's like natural numbers, but you can go the negative direction as well. So you can have negative and positive, but the whole idea is that they are whole numbers. There's no decimals, no fractions, or anything like that. Okay, the whole numbers. So n is natural numbers, z is integers, then q is what we call the rational numbers, or the list of rational numbers. Because notice all what I've written here is list, right? So it's a list of a certain type of number. Okay. So Q then is rational numbers. That basically is a fraction. Okay. So this is a number of the form a over b, uh, which uh, which a and b are integers essentially. Um, so for example, we could have um, 2 over 3. We could have negative 4 over 9. That's fine. You can have negatives as well. You could have 16 over, I don't know, 157. You know, the whole idea is the top and the bottom are whole numbers. We can also have, for example, 5 over 1. Okay, but that would obviously go to 5, uh, which should be a natural number because 5 would be in this list. But the whole idea is it's a rational, it's a fraction with the integers, with both integers on the top and bottom. Notice I say integers, so both the top and bottom a and b have to be in this list here, the list of integers. So at the top and bottom of the fraction are essentially whole numbers. Um, and also you can simplify it as well. So, for example, 4 over 6, we can have. Obviously, that's the same as 2 over 3. But both of them are completely legitimate, right? They're both rational numbers. Doesn't matter if you simplify. Doesn't matter if you have it over 1, like in this case, and it simplifies to 5. The whole point is it's expressed as a fraction, which both top and bottom, the numerator and the denominator, are whole numbers. Okay, that's all it is to it. Okay, that's all that is. Rational numbers. Um, and yeah, and this last bit R is reals, and these are real numbers. So this is essentially every number you can think of, essentially. So basically, a real number is irrational and irrational as well. Now, the irrational numbers, we looked at an example of this with surds, right? So, for example, that would include stuff like root 2, because root 2 is a third and that's an irrational, which essentially means if you put that in a calculator, root 2 for instance, you would get a repeated ongoing decimal forever. We can't write it down as a whole because it's just an infinite decimal. But it's root 2, which is an irrational. Again, so it includes irrational and irrational numbers. So root 2, but also irrational, like again, like negative 3 over 7. That would be a real number. Pi, uh, pi squared over root 3. That's a real number, so it's irrational, obviously, because the top and the bottom are not integers. But it's a real number, nonetheless. And essentially, the real numbers you can think of as a number line, right? Stretching from like negative infinity, oh, all the way. Say if you have 0 in the middle, all the way to infinity, and you can have absolutely any number in between, right? So this would be what we call a real number line. And so basically, it's absolutely any number you can kind of think of, right? Um, and yeah, that's essentially what real numbers are. So basically encompasses every of the other three lists of numbers. So the natural numbers, the integers, the rational numbers, but also irrational numbers like pi and root 2 and thirds and so on. Okay. And yeah, so that's all there is to it. So those are the four lists of numbers you can think of. The four lists of numbers we work with. Usually those are the main type of ones. Hopefully you notice as well. Uh, that the more we include more lists of numbers, we include the ones before it as well. So for example, with integers, notice how we have the negative in whole numbers, but we also have the natural numbers as well. So the list of integers z includes all the natural numbers n. In the same way, Q, which is the rational numbers, includes all of the other two, the natural numbers and the integers, because A over B, again, say for example, we've got -3, which is an integer, we could have -3 over 1. So it basically it includes everything before it as well. So it's almost just like going up and up and up and basically it's just including more and more type of numbers rather than excluding stuff out. You know what I mean? So we can basically branch out and include more types of numbers, and then real numbers include the rationals, which obviously then include the integers and natural numbers, but also irrational, like pi and √2. That's it's important to go over that now because you will see those symbols crop up fairly often in the A level in pretty much any type of topic that you come across. It's quite a fundamental topic. So I thought to go over that quick now because you're going to see examples like here where we have this funny R symbol. And now hopefully you know what R means. So it's a real number, which is essentially absolutely any number you can think of. You can almost think of it as a number line, right? So a number line included absolutely any number. Okay. So why am I going over this in this section? Well, it links back to this idea of domain and range. So again, as a recap, domain is the numbers in a function we plug in. So at x, we plug in the next value, then we get the range, which is the output. Okay. Now, why is that important? And I wrote this down here because this symbol here, what this symbol means, it means exactly. It means is a member of. So, for example, if we said x and this symbol and then here, this sign here, that's saying a value of x, which is a member of uh, the real numbers, right? So value of x or x value or just x. So it's what this symbol saying x. Oh, x then, and then this e symbol almost. X is a member of, and then this r means real numbers. Okay. Um, So what this is essentially saying is the value of x, which belongs to the list of real numbers, right? So remember, real numbers is kind of like a list. We can go from a negative infinity to infinity of every value in between, right? So it's saying basically, if x is a member of the real numbers, then it can be absolutely any value, right? Because it's a real number is essentially any value. So we could pick x, we can just pick as a value from a real number. Um, okay. What if instead I said, do, 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 do. What if I said instead x is this, where x is now a member of this n shape here, this n shape, this n letter. That's going to correspond to the natural numbers. That's saying n has to be a member of the natural numbers. So the part of, so it has to be in the list of natural numbers essentially. Well, that means x has to be 0, 1, 2, 3, 4, or so on. But what that doesn't mean is x can't be pi or x can't be -8. Because remember, then that's not a natural number. Natural number is this list here, which I highlight here. Okay. Um, so that's telling you what this is eventually telling you is we can use this sort of notation to tell us what values of x we're plugging in. So again, for example, if x was a natural number, then if we had f of x was again x squared, well, what this is saying is we're only plugging in natural numbers, okay? Because x has to be a natural number. That's what this is saying, okay? So for example, then our domain in this case would be 0, 1, 2, 3, 4. Those are the values we're plugging in, okay? Because it's a natural number in this case, because that's here, right? So it's a natural number, okay? And therefore the range is, in this case, well, f of x is x squared, so we're going to square our domain, square our inputs. So the range, well, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. Okay, that is essentially the idea of domain and range, and this is and you're going to start seeing these symbols and this notation crop up in the questions, because why this is useful is it's telling us what domain we want to use. So what list of numbers do we want to plug in to our function? To echo what I just said, usually it's these list of 4 numbers here. Okay, these are the 4 most common type of numbers. These are the symbols you do need to recognize. We have to know what they mean. But hopefully the idea isn't too complicated, right? Natural numbers, positive whole numbers, integers, just whole numbers in general, so it'd be negative as well. Rational numbers is a fraction with integer top and bottom parts. And a real number, it's absolutely anything you can think of. So it can be pi, it can be root 2, absolutely anything. Okay, and that's it. Okay, and that's domain and range. So, without going into any more detail to try to overcomplicate it, let's just jump into some questions to explain this whole idea. Okay, so we are given a function, two functions f and g. We're given f of x is 2x minus 10, and g of x is x squared minus 9. And we're given this symbol here, X with this weird like E-ish E shape, which means it's a member of, or it's a member of, or it's a part of essentially. Uh, it's R, which is a real number, right? So X is a part of the real numbers. So X has to be a real number. So essentially, X can be pretty much anything then, right? As it's a real number. So it's this little number line kind of thing here, between negative infinity and infinity. Okay. Okay, so that's what that symbol means. Then part A is telling us to find the values of f of 5 and g of 10. Well, f of 5, that's telling us our input is 5. We want to input 5 into our f of x here. So plug in x is 5. So that's going to be 2 lots of 5 minus 10. And so therefore that would be 10 minus 10 equals 0. Therefore, uh, when the domain is 5, that what this is saying, the range is 0. Okay, so when I input 5, I get out 0. Okay, so the input is 5, the output is 0. Or when the domain is 5, the range is 0. Okay, so and when you start to get used to that sort of language. Okay, likewise, it's asking for g of 10. So we're going to plug in a 10, which is our input into our g of x expression here. So g of 10 is going to be 10 squared then, minus 9. Well, that's going to be 100 minus 9, which is 91. Okay, and again, to reinforce what I'm saying, 10 in this case is the domain. So when the domain is 10, so when we pick 10, then we get out 91. So the range will be 91 when the domain is 10. Okay. So yeah. Then for part B then, cool. Find the value of x for which f of x is g of x. So f of x is g of x. Basically, we just need to equate this with this, right? That's what that's saying. So our expression for f of x, which is 2x minus 10, has to equal the expression for g of x, which is x squared minus 9. But how are we going to solve this? Well, if we move everything, let's move everything to the right in this case, because we have an x squared here. But you don't have to. But then with x squared then minus 2 of x, because we're going to move the 2 of x onto the other side. So I'm going to take away 2x. Then I'm going to add 10 to both sides. So plus 10 minus 9, that'll go to plus 1 equals 0. Okay. How to solve this? Well, it's a quadratic, isn't it? We know how to solve quadratic. We looked at that earlier. Let's try factorization. Well, we want a time to get 1 and add to get minus 2. Well, the only factors are 1 and 1 and 1. So, if we want to add to get minus 2, we're going to need minus 1, aren't we? As our two factors. Because then that times to give 1 and add to get minus 2. So it's going to be x minus 1, which is 0. Or you can recognise that as x minus 1 squared, but it doesn't matter. But clearly x is 1 is the only solution here. Okay. and I want to reinforce the language again to make you get used to it. When we have a repeat, what we call a repeated solution here, is obviously when the same factor, the same bracket crops up twice. Okay, so we call this a repeated root or a solution, right? Repeated root solution. When a solution crops up in this way, when we somehow get the same factor twice. Okay. So yeah, but yeah, that's our solution, right? And so, how would we say that in our language we just learned is uh, the 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 domain when the f of x and g of x is one. Okay, so when x is one, when the input is one for both functions, when the domain is one, then that's when the two functions equal to each other, or when the range is equal to both functions. Okay, but yeah, okay. Let's have a look at another question then. Okay, we are given f. The function f is defined as f of x is x squared plus 6x minus 5, and again, it's telling us it's x is part of or is a member of the real numbers. So again, x is a real number, so that's basically anything. Okay, that's for telling us what we work with. Usually, it's going to be x is a real number. Usually with functions, so you don't have to worry, but that's what that means. Okay, so let's write our function down is x squared plus 6x minus 5. First of all, it's asking us to write f of x in this form here. You should notice that is completing the square because I have a bracket of x squared, right? X plus something squared, add a number. That's completing the square. So we did this last time, right? So complete the square, we're going to have x, a bracket x, and then you're going to halve the 6 to get plus 3, all squared. Then take away 3 squared, which is minus 9. Then we have the minus 5 at the end. Then that'll go to x plus 3 all squared. Take away 14. And there we are. That's written in that form now. Cool. Then for part B, hence otherwise find the roots of f of x. Okay. So the other bit of language you need to know is you might all be familiar with it already, but when we say of a root of a function, that is the solution um, to f of x is equal to 0, right? So if we set the function equal to 0 and we solve it, that tells us our root, okay? So that's what we're going to do. So the root then, it's going to be when f of x is equal to 0, right? But this is also f of x, what we worked out in part A. So simply x plus 3 squared minus 14 is equal to 0. Then the root is a solution to this equation. So we're going to solve it. And again, we looked at solving it equations like this earlier on in the chapter. So you can firstly add 14 to both sides. So we get x plus 3 all squared equals 14. Then I have a square number, so I can square root both sides, so then get x plus 3. But that's plus or minus the root of 14. Okay. Then I can take away 3 to both sides. Then x is minus 3 plus or minus root 14. Well, that's our solution then. So therefore, the roots of the function are minus 3 plus root 14 and minus 3 minus root 14. Okay, so it's basically this whole section is all the concepts you used before, all the ideas you know before. There's nothing really new, but it's the language you need to get used to, right? So here you need to recognize a root is the solution when you solve the equation equal to 0. Okay. But yeah, then for part C, write down the minimum value of f of x. State the value of x which it occurs. So we looked at this briefly at the end of the last section, completing the square. It's if we complete the square, so let's rewrite what we have. X plus 3 squared minus 14. But when you have it in completed square form, it can tell you what the minimum value is of the expression because this is a square number. We know that a square number cannot be negative, so it has to be at least 0. No, so no matter what value of x you plug in into x plus 3, if you square it, you get you have to be at least 0, right? because a negative squared will also be positive. So negative cannot happen. So that's telling you the minimum value has to be at least 0. But then we're minusing a 14, right? So, if it's at least 0, then we're minusing 14. That means the minimum value is equal to minus 14, okay? Because a square number has to be at least 0, right? Um, because, for example, root 0 is obviously 0, that's smallest. But then if you did root minus 1 and root 1, if you go to the negative, hang on. No, sorry. 0 squared is 0. But then if you had 1 squared and then minus 1 squared, there we are. Root, you can't square it a negative. If you had root of minus 1, well, that'd be 1. And 1 squared is also 1. So as you see, 0 in the middle is the smallest value when you square it. But if you have negative squared, if you go to go negative, it will also give us a positive. So actually, 0 is always the minimum value of a square number. Okay, so the minimum value has to be 14 because we're adding on a minus 14 after the square number, and then it's asking for the value of x when it occurs. So when is the minimum value 14? Well, it's when this bracket has to equal 0, because then I have 0 minus 14. Okay, well, that means then x plus 3 has to equal 0. So x is minus 3, and that's it. Um, cool. We will look at more of this later, the next chapter actually, to do with minimum values of completed the square. We will look at this in more detail next time, but hopefully you recognise the logic we've done here. Okay, it's not too dissimilar to what we did last time. Okay, when we looked at how things can be positive if you complete the square. Anyway, um. Okay, again, look at this example then. It's asking to find the roots of this function. So again, going back to last time, the roots are when the equation, the function equals 0. So our function's x to the 6 plus 7x cubed minus 8. That has to equal 0. And so we need to solve it to find the roots. Okay, but actually, how do we solve this? Well, it's not quadratic explicitly. But again, this is what we call a disguised quadratic, isn't it? Because I recognise, well, I have x cubed here, but x to the 6 is the square of x cubed, right? Well, if I then say u, for example, is x cubed, then I could substitute that in for x to then get the equation, well, x to the 6 would be u squared, right? Because x cubed, the square here is x to the 6. So I have u squared plus 7u, because again u is x cubed, minus 8 equals 0. And now I have an actual quadratic, right, which I know how to solve. So remember, we call this a disguised quadratic when we can convert it or transform it into an actual quadratic, okay? We looked at that in the first section when we looked at solving quadratics. We can solve more complicated equations by making it into a quadratic, like in this way here. Okay, so we can solve this then. So I think I can solve by factorising, right? So I need to consider the factors of 8, which should be 8 and 1, for instance. Well, I need to add to get 7. Well, I can do that, can't I? Because 8 minus 1 will get us positive 7. But I need to so I need the time to get minus 8 and then add to get positive 7. So I'm going to do 8 and minus 1 as the factors. So u plus 8, u minus 1 equals 0. Again, if you're a bit unsure of that, make sure you know how to factorise. Again, we looked at it earlier on in the earlier one in the first 2 chapters. Okay, we looked at factorising in great detail in the first chapter, which I've done a video on. So yeah, we can factorise it in this way. Um, and so therefore the solution is when each bracket or each factor equals 0. So u is minus 8 or u is 1. So those are 2 solutions, but that's solving for u. Remember, we need to solve for x. So we need to bring this substitution back in to get x. So then if u is x cubed, then x cubed is minus 8, or x cubed is 1. Then to get x, I can cube root both sides. So x would be the cube root of minus 8. Remember, we can do this with a negative because we're not. It's not square root, it's a cube root. Because this is saying what number cubed gets minus 8, but obviously if you can cube a negative and get a negative. Because a negative 3 times is still negative. But then if you should spot that's minus 2, okay? Because minus 2 times minus 2 is 4, but then 4 times minus 2 will get us minus 8. Okay, so that's one solution, or x then would be the cube root of 1, which would just be 1. Okay, and there we are, that's our two solutions. So these are our roots then. Okay, so roots are minus 2 and 1. Cool. So the roots then are the parts of the domain at the inputs, right? Such that f of x would equal 0, right? So in other words, the roots are the inputs, right, the x values, which gives a range of 0. Okay, if we were to use the language that we used earlier, I'm just trying to, really just trying to keep repeating what the language you use. So hopefully at the end it really sets into your mind, and so you get really comfortable with the terminology. Um, but yeah, these are the roots, right? Essentially the values where we get 0 when we put into f of x. Okay. So that's really most of it. So at some more exercise questions then. So have a look at this one. It's given that the function f of x is defined by f of x is x squared minus 2x. Again, x is a real number. That's what that means essentially. Given that f of a is 8, find the two possible values of a. So this is telling us then if we input some number a, we get 8. But we know what f of a is if we plug that into our expression here for f of x. Well, that'd be a squared minus 2a equals 8, right? Because f of a is when you plug a for x into here and into here, right? Because then x squared minus 2x will become a squared minus 2a, and it's told us is equal to 8. Okay, and again, if we were to use our language earlier, when the domain is a, the range is 8. Okay, I really want to keep drilling that in. So then we need to solve it because that's going to find the value of a. Well, if we move 8 to the other side, we get a squared minus 2a minus 8 is 0, because that gives us a quadratic. Cool. So then if we solve it, perhaps by factorising again, we need to consider the factors of 8. Well, either 8 or 1, and then 4 or 2. This is great because we need to add some way to get minus 2 to coefficient on the just a. So how are we going to get minus 2 by adding these? Well, you're going to get minus 4, aren't we? Minus 4 and positive 2, because then minus 4 add 2 would be minus 2. And if you times them, you get minus 8, which is what we want as well. So that's our factors. So we factorise to a minus 4, a plus 2 equals 0. Then each bracket has to be 0. So a is 4 or a is minus 2. Cool. So those are two possible values. So again, to emphasize, when the domain is 4 or minus 2, then the range is 8. Okay. Which again means when the input is 4 or when the input is minus 2 into the function. When we plug those two values in the function, we get 8 at the output. Okay, just to make sure we're comfortable with the language there. Okay. A final question here. We are given two functions, f of x is x dots of x minus 2, and g of x is x plus 5. It's told us that when f of a is equal to g of a, so that's telling you when you plug in a number a into both functions, they are equal to each other. So we can plug a in to both functions directly, but then that's saying a lots of a minus 2 is equal to a plus 5, okay? And it's asking us to find the value of a, so we need to solve this, right, to get a solution for a. The best way really is just to expand first of all the bracket probably. So that'd be a squared minus 2a is a plus 5. Then we can move this whole right hand side to the left to get a quadratic. Then we get a squared, take away 3a because we have minus 2a, take away the a from the other side. Then we're going to have minus 5 equals 0. Cool. Again, we could solve this. We could factorize, but an exam tip here. It says give the value of a to 3 significant figures. That's telling you there's probably going to be a decimal involved, right? So do not factorize because you're going to get an ugly factorization, which you can't do. You, you can't really do mentally. Um, so really, quadratic formula, right, is probably the best way to go. So a then. Remember, it's going to be minus of minus 3, plus or minus the square root of, just recall as well, the quadratic formula is x minus b, plus or minus square root of b squared minus 4ac over 2. I remember we did that in the first part of this chapter when we looked at solving equations, where a, b, and c are the coefficients of the quadratic. So here, the coefficient of the a squared is 1, the coefficient of the a is minus 3, and the coefficient, the number at the end is minus 5. So we get minus lots of minus 3 plus or minus square root of minus 3 all squared, minus 4 lots of 1 of minus 5 over 2 lots of 1. Then if you put that into the calculator, you would get do, 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 minus. You get these two numbers here. A is 3 plus or minus the root 29 over 2. And yes, see, we've got a really ugly, what's it called? Answer here. We would not be able to factorize. Or we could complete the square actually, but I'm lazy. I want to use the quadratic formula. So we've got this value of a, so it's 3 plus root 29 over 2, or 3 minus root 29 over 2. But it's asking us then to give it to 3 significant figures. So really, you need to convert this to a decimal. So then either a, well, 3 plus root 29 over 2 is 4.1925 dot dot dot, or a 3 minus root 29 over 2 would give me minus 1.1925 dot dot dot, and then we need to give that to 3 significant figures. So that's going to be 4.19, but then 2 would keep would mean we do not round up, so we leave it at 4.19, or a is minus 1.19 to 3 sig figs, and there we are. Okay, but then if we look at the question again, though, it, it's said to find the value, so it's saying we need one particular value, but we've got two here. But it's asked us, it told us this as well. A is greater than 0, so A has to be positive. But here I have a negative and I have a negative and a positive, so we want A to be 0. So the only solution here is A is 4.19. So not this one. Because that's a negative. So actually, that's the only singular value in this case when a is greater than 0. Cool, cool. There we are. And that's really it with functions, right? So there's actually nothing there's nothing procedurally new we've done there. Like, again, we're just finding roots. So we're solving quadratic equations like we know how to. We complete the square. We've done all that before. We've done nothing. There's nothing new actually with this function, but the language that's new. So what f of x means, what f of a means, what this symbol means. For example, x has to be a real number, which is what that means. What the type of numbers are, right? So again, go back here. These four lists of numbers commonly used: natural numbers, the integers, the rational numbers, the real numbers, and also the idea of what a domain and range means, right? So what the values we plug into a function is a domain, and what we get out of it when plugging in the domain, our input, is our range. Okay, what we get out of the function. And that's essentially all it is, right? That's essentially all you need to know. But yeah, I'm going to leave that there then, and I'll see you next time.